I'm sure we were discussing this, if I remember correctly, at the very beginning. Like, you know, you wonder like how your digital computer phone plays the analog audio. You know, even as I'm talking, everything is being digitally processed, but you don't hear on your end a sequence of zeros or ones, right? Or you don't hear numbers. You basically see or hear the audio signals. But there's a conversion process going on in the middle. So how is that happening? Well, OPAMP can actually also be useful over here. And these devices are basically referred to as digital to analog converters, known as the short form for it is DACs, okay? Digital to analog converter. So say you have a song in a .wav format, right? You have some chunk disk here, some format description over here. These are some numbers in hex format. Remember, it's a hex format. The core, the meat of the song is basically everything that you see in green, okay? So this is one sample, 64. Then this sample arrives. It is converted into audio signal. Then this sample, this sample, this sample. So it goes like this, and then it starts from here again. It keeps on doing that. And when it plays these numbers, remember, these numbers represent some binary values, and then those values are then converted into an audio signal, and that's what DAC is doing. So for example, if you take this number right here, F9 here, F9, remember this is a hexadecimal, so the base is 16, okay? So this would basically mean in a binary format, what is the code for 9? Does anyone remember that? What is the binary code for 9?
1001.
1001. So just in case, just a quick, I don't want to spend too much time on it because this is something that is expected. I don't expect you to know at this point, but I think most of you should know it. In case if you don't know it, we get to a binary sequence for any number by just simply dividing it by 2 and then keeping track of remainder. So 2 times 4 is 8, remainder is 1. 2 times 2 is 4, remainder is 0. 2 times 1 is 2, remainder is 0. We stop when we get to 1 here, and then we cannot further. You know, so we take the sequence right here going from bottom to top like this. We go this way. So 1, then we have 0, 0, and then there's finally this one right here. So that's a binary code for 9. Similarly, F represents 15, and the binary code for 15 is 1111. So here is an 8-bit code for this sample F9, okay? And if you want to convert this, again, this is the binary representation. If you want to convert this into a decimal representation, then you basically add the magnitude of each individual bits. So this bit right here represents 1, 2, 4, 8, 16. This is 32. This is 64, and this is 128. Okay, so you only add the numbers for which the bit is set to 1. So 128 plus 64 plus 32 plus 16 plus 8 plus 1. Okay, I'm not adding this 2 because the value is 0 here for those two. Can anybody do the math real quick for me? 128 plus 64 is how much? 96, 112, 120, 121. Is that 229?
I got 249.
249? Okay, all right. 249. So this sums up 249. And this is the decimal representation of it. Okay, remember the data can be represented in different ways. This is the binary representation right here. This is the decimal representation. And originally the data was in a hexadecimal format. Okay, now let's look at this circuit, how this whole thing is working. Okay, we have a DAC here. We have a DAC here, and it's got 4 bits, B0 right here, B1 right here, B2 right here, and B3 right here. Okay, and then this is a VREF. In other words, you could just think of it as VS or VCC, right? This is some source. Usually it's anywhere between, you know, can be anywhere between 1.7 to 3.3, or sometimes it's 3.3 to 5 volts, anywhere between those range. Okay, all right. And what's going to happen is this DAC may look from inside. What goes, it comes in a chip side. Okay, this is DAC. It's got pin over here. Okay, inside what you have is basically this thing. Okay, inside this chip you have the everything that is in purple. Okay, all right, now if you look at it, because this is a 4-bit B0, B1, B2, B3, which is basically this right here, 2 and B3. Okay, all right. Each bit can either be 0 or could be 1, right? Binary comes from binary digit. Okay, so you take B from here, you take IT from here, that makes bit, and 1 bit can either be 0 or could be 1, right? So this number, or whatever this B0, B1, B2, B3, it will make a sequence of zeros and 1. So say if B0, if you focus over here on this red box, B0 is connected to this node right here, and this node is just simply connected to ground. Can you tell me what is the value of B0 here?
0.
I told you anything that's connected directly to the ground will have a value of 0. 0 volt means 0 in binary. If I change this to something like this, then what would happen? The B0 will equals to
1.
B0 is connected to VREF. VREF is going to be some voltage in this range. Anything in this range is going to be considered as 1. So this will be 1 this time, right? So whatever the values of B0, B1, B2, B3, this part of the circuit will make arrangement for that. Okay, this will reflect whatever we have at B0, B1, B2, and B3. Okay, cool. Now let's move on to this part of the network. Resistors. We have at the bottom Ri, we have 2 Ri, and then everything above that is multiple of 2. 4 Ri, 8 Ri. And one reason I want to explain that, maybe I can use the digital. So there are 3 numbers on the screen, right? 407. If I ask you which is the greater number, what would you answer? You got 4, 0, and 7. Which number is a greater number here?
7.
7. 7 is a greater number here. But if I say 407, then you know that this number here represents ones, this number represents tens, this number represents hundreds. So even though 4 is smaller than 7, but it has higher significance because it represents the 100. So 4 over here represents 400, whereas 7 represents 7 over here, correct? Right? Each digit has its own sequence, the way it is arranged. Similarly, in a binary number, say this is some 4-bit binary number, 1101. This has its own significance. This one has its own significance. The significance of the number increases as you go to the left. Notice over here what we were doing. When we were mapping these values over here to get a decimal representation, the numbers were increasing as you were going to the left. the leftmost bit, which is this bit right here, this had the highest magnitude. What was the magnitude of this bit?
128.
128. This was 64. So this in digital systems is referred to as the most significant bit, which is the leftmost bit. And this on the very right, whatever that bit is referred to as least significant bit, LSB, which basically tells this has very less significance compared to the most significant, which is on the very left. Okay. All right, let's now go over here. And maybe since we are already here, as we move from right to left, do you see a sequence at which the magnitude is increasing? It's doubling every time, right? 1, 2, 4, 8, 16, 32, 64. Now, if I take you back to this circuit, do you see that sequence over here also? Right. So, and I'm going to ask you one question here. Over here, B0, B1, B2, B3, which is the least significant bit here?
B0.
B0, which is the rightmost bit, is my least significant bit here. And therefore, you see 8 Ri here. B3 is the most significant value. This is the highest value that you can get. That is represented as Ri only, right? So in other words, what's happening over here, I'm going to take you back over here and I'm going to rewrite because it's little 128. This is the least, most significant bit. 64, then we have 32, then we have 16, then we have 8, then we have 4, 2, 1, and 0. Okay, so say this is B7, B6, B5, B4, B3, B2, B1, and B0. We're not going to have 0. It's B0 here, right? So these are how many bits? These are 8 bits right here. Okay. When we go from here to here, we divide it by 2. When we go from here to here, we divide it by 2. When we go from here to here, we divide it by 2. Similarly, that's exactly what we are doing. Okay. Imagine this Ri is connected to your B3. That's B3 is your most significant bit, which is 128 here. So the next is going to be divided by 2. And that's what we do. It's going to be 2 Ri. And we're not dividing it actually here. We just putting the value of the resistor, which is twice as big as it was over here. And it'll just keep on increasing by 2 every time. Okay. So say if I make it a 5-bit system, if I make this whole thing, let me erase this, not a 4-bit, but a 5-bit system in which I'm going to add one more bit by say, and then, so what is the value of this R right here?
16 R1.
16 R1. 16 R1. Good. Okay. All right. And pretty much this part is, we have done so many times here. You can tell VP is equals to 0. That means you got Vn equals to 0 as well. We're going to build upon it on over here now. And this was another thing. What kind of a circuit this looks like? Does it look like a summing amplifier? Does it look like a differential amplifier? It looks like a summing amplifier. It is absolutely similar to summing amplifier, except for we have this one for VREF and one for ground. But other than that, it is very similar to a summing amplifier. So what was the output equation of the summing amplifier we just drove? Anybody remember? Let's go to that was the first example, right? What was the output equation? Minus RF over RI, and in bracket we got V1 plus V2 plus V3 and so on, V plus V4, whatever, how many numbers of we have. So I'm going to apply that same thing over here. Here also, say I'm gonna have to assume here Vref, say Vref is equals to 1.28 volts, okay? And then you are asked what is V naught for V out for the given. Okay, and so we have to find out V naught here. While we are going to find out the V naught, can we find out B naught, B1, B2, and B3 here first? What would that be? Looking at the circuit. Look how the way the connections are made. What is that binary number that you see?
1010.
1010. B3 is 1, B2 is 0, B1 is 1, B naught is 0. And again, B naught is 0. Why? Because B naught is connected to the gray wire. Gray wire is directly connected to the ground, hence it's 0. If you look at B3, B3 is connected to the white line, and white line is basically Vref. Okay, and Vref is 1.28. So this is going to make a logic of 1. So therefore, we have B3, B2, B1, B naught as V1010. Okay. Can I go down a little lower because I might need more space? I can just for the summing amplifier, the equation that we got for V out was something minus RF over RI V1 plus V2 plus whatever Vn, something like this, right? I'm trying to give a similar representation to this equation for V out. This is gonna be V out equals to minus Vref here, and then Ri over Ri times B3 plus Ri, feedback resistor Ri right here, over 2Ri times B2 plus Ri, which is a feedback resistance, over, I'm trying to put it in this format, right? This format, Rf over Ri. Rf is Ri, and Ri this time here will be 4Ri times B1 plus I have Ri over 8Ri times B naught bracket close here. Okay, all right. Now I'm gonna keep minus Vref as it is. Ri and Ri will cancel, so this will be just simply B3, correct? B3 plus over here Ri will cancel, so I'll get 1 over 2 B2, correct? Here I'll get plus 1 over 4 dot B1 plus 1 over 8 dot B naught, right? Okay, because I know the value of B3, B2, B1, and B naught, let's put those values. B2 and B naught are 0. B2 and B naught. So this whole term will be 0. This whole term will be 0 because B2 is 0 and B naught is 0 as well. So if I rearrange this equation, then I get what? V naught equals to minus Vref. This will be 1 plus 1 over 4 is 0.25, correct? And then Vref was how much? 1.28 volts. So a negative sign outside, 1.28 times 1.25. Can you guys do the math for me, folks? 1.28 times 1.25. What would that number be? Negative 1.6, right? Yeah, negative 1.6. So V naught will come down as negative 1.6 volts. What does that really means? Well, it means at the output, when we are getting a data which is 1010, as it was, this was a digital signal in binary. It is equivalent to saying negative 1.6 volts in an analog world. Okay, and now again, we can convert this negative 1.6 volt into some audio signal. And that's what this DAC is doing. It's converting that back, the digital number, into an audio. Okay, remember what's going on, how this music is played. Well, as I'm speaking here, I'm basically, the whole audio signal is being converted into a sequence of zeros and ones. It could be 8-bit. Usually it's 8-bit. The higher the number of bits, the higher the resolution, the better it is. Okay, so 8-bit is pretty standard. 16-bit, you take it to the next level. And so the more you break it down, my voice is basically broken down into very small intervals, which are represented by some magnitude. In this case, it's going to be a voltage, but it can also be a current. And this voltage represents a certain sound